All right, we're going to try this again. Hopefully the recording software doesn't fail out. Okay. All right. So what we're going to do is we're going to take our knowledge so far and we're going to extend it into linearly distributed loads. So to be clear, we're using the same mathematical expressions we have so far, the same relationship between loads and shears and moments. The idea that between loads and shears, if I integrate my load diagram, I will get a shear diagram. And if I integrate that shear diagram, I will get a moment diagram. And really, those are just fancy ways of saying that at any given point, the slope of the shear diagram is equal to the load, and that between any 2 points, the change in shear is equal to the magnitude of load. And we can make similar observations for moments that between shears and moments. Now, what we're going to do is look at triangular loads. Triangular loads, we're going to run into a problem, okay? And here's what's going to happen. So we use that same integral relationship, and we find that our loads are going to be linear, okay? And so if we integrate a linear function, we have quadratic shears, and if we have quadratic shears, we have cubic moments, okay? Our graphical approach is not going to work very well to determine quantitative areas. Now again, I throw triangular loads out there because we do see them in the real world. We talked about hydrostatic forces. How many of you are in fluids right now? So if you're in fluids right now, you probably already dealt with hydrostatic force effects. You have a wall, you have a triangular load on the wall that as you get deeper, the pressure increases. Have y'all done that already? I imagine that that's already happened now in fluids. And then we also have snowdrift. So we do have triangular forces that we have to deal with in the land of civil engineering. So we need to be able to deal with this too. But again, that quantitative data is going to be difficult to determine. Now, like last time, we're going to have a geometry problem. So I kind of want to handle the geometry part first, and then we'll look at the actual structural analysis here in a bit. So let's look at our geometry problem for today. We are not looking at azimuths. Let's go back. Let's go to structures. Okay. All right. So I have here a beam that is subjected to some triangular load. Let's say it's 0 to 4 kips per foot. So the peak of that load is 4 kips per foot. And what I'm doing here is I'm cutting a section through the load. So I'm cutting a section at some arbitrary distance, we'll call it X, from the end of the load. So we're talking about a beam. Let's say the beam is 35 foot long. It goes from 0 to 4 kips per foot, and I'm cutting a section right here. Okay? So the idea is I need to determine, so I'm drawing a free body diagram, and just like with uniformly distributed loads, what we'd like to do is we'd like to collapse that into a single concentrated load, and we'd like to figure out where to put that load. Okay? So again, the idea is that we have samurai sorted or lightsaber. Ooh, let's draw. Oh, you're kidding. Well, this is going to be upsetting. Let's try that. There we go. That's better. So the idea is that we're samurai sorting right here, and I want to be able to quantify this force into a magnitude and a location. So first off, let's be clear, this distance is x. Okay, so let's handle the simple part first. If this distance is x, what is this distance? The distance from my section cut to the concentrated force that's statically equivalent. How far is it from here to here? If this is x, what's that distance? A third of x, right? It's a triangular load. So this distance right here, so d in this case, is going to be x over 3, okay? That part is pretty easy, right? Now, I think probably the most difficult part is figuring out the magnitude, okay? Now, let's just keep in mind that the magnitude is going to be, so I'm going to put this up here, we'll put this on top. The magnitude is essentially going to be the area of that triangle, which is 1/2 base times height. Okay, so 1/2 base times height. So what is the base of this rectangle? The base of this rectangle, or sorry, this triangle, the base of this triangle is x, right? And the height of this triangle, I'm going to try and figure that out, okay? So we'll call this, we'll erase this, and we'll say 1/2 x, and we'll call it h, okay? Now I want to express everything in terms of x. This term h, I don't want multivariable. I want just a single variable. So I want to see if I can express h in terms of x. So how do I do that? Well, I propose that the simplest way of doing that is just to use slope ratios. Okay? So how do I determine h in terms of x? Well, it's just a rise over run problem. So I propose that for every 4 units that we rise, we go over 35 feet, right? Does everybody see that? So this diagonal line, I go up 4 and over 35, right? So if I go up 4 and over 35, the question is, how far do I go up if I translate some distance x? So it's just a ratio problem. I have 4 over 35 equals some height over x. So therefore, I can say the height is just 4x over 35. And for the sake of discussion, we're going to sort of assume everything is in consistent units, so I'm not going to get too worked up over making sure that all my units are written here, because everything's going to be in a consistent unit system. So what I can do is I can say, all right, I've got 1/2 x, and then instead of h, I've got 4x over 35. So, it's supposed to be 35. So that's going to equal, what is that? 2x squared over 35. Did I get that right? So now what I can do is I can write this as 2x squared over 35, and that's going to be my force, and that's going to be my moment arm. Does that make sense? Is that okay? So if I cut a section at some distance x away from this support, I can take this triangular load and idealize it as a single concentrated force that's 2x squared over 35, and the distance from the section cut is x over 3. Is that okay? That's not incredibly challenging, right? Okay. I want that part to be clear because we're about to do an actual problem, and I want to make sure that part is simple. Sound good? All right. So, actually, let's just do it in the notebook. That'd be easier. Okay. So this is going to be the problem that I want to look at. So we're going to draw the shear and moment diagram for this beam. Okay. And I have a beam that's 30 foot long, and it has a triangular load. Okay, that triangular load goes from 0 all the way to 2 kips per foot, and I haven't given you the reactions. I haven't done that yet, okay? So we need to compute the support reactions, and we need to see if we can construct the shear and moment diagrams. We're going to see something kind of interesting with this, okay? But before we do that, let's walk before we run. Let's see if we can determine the support reactions, okay? So first off, if I want to determine the support reactions, I need to take this and collapse it into a single load. If I take this load here and collapse it into a single force, how much is that force?
30 kips.
30 kips. And how far, let's say how far from B does it go? 10 feet, okay? So I've got a turn my little pen thing on. There we go. So that's 30 kips, and then this distance, we'll just do it down here. This distance is 20 feet, and this distance is 10 feet. Okay? So what I need to do is I need to, this part's pretty easy, right? So I'll just sum moments at A.
Should that be 60 kip instead of 30?
Oh, let's talk about that. Why would it? Well, how'd you get 60?
2 kips per feet. Oh, wait, it's a triangle.
It's a triangle. That happened on the last celebration. I saw that happen a couple times. There was a triangular load. You got to cut that in half because it's a triangle. Yes, you got to cut that in. That's 30 because you got to cut that in half. All right. So maybe I'll do 1/2, 2 kips per foot times 30 feet equals. Okay. So summing limits at A, I've got 30 kips times 20 feet has got to be balanced by BY at a moment arm of 30 feet. So 600 foot kips is BY times 30 feet. So therefore BY is plus 20 kips, which is 20 kips upwards. And so if that's 20 kips, then summing forces in the Y direction makes AY 10 kips upwards. Is that fair? That part should be easy. Okay? All right. Everybody with me so far? Okay, so let's go through our graphical approach exercise. Let's see what we get. We're going to see our problem real quick. Okay, so let's make sure we're clear. This is AY is 10 kips, and this is BY is 20 kips. Anything else that you think I should disregard when I draw my shear and moment diagrams? This, right? This was a construct that we created to make the computation of support reactions easy. But that's not what's really going on in the beam. What's really going on in the beam is this linear load, right? So I think what I'm going to do is, does everybody have this info up here? I'm going to take this and I'm going to erase it. This doesn't exist. This is what's going on the beam. Okay? All right. So, oops, scroll the bar a little bit. Okay, so let's see if we can draw these out. Okay? So here's my beam, or here's my horizontal line. We'll call this shear in kips. Okay? So let's get the broad strokes out of the way first. Okay? So I'm going to start at 0. What's the first thing I'm going to do? Jump up to 10, right? So I'm going to start at 0. I'm going to jump up to 10. And I'm going to get, this is 0, this is 10. Okay, so after that, what's going to happen? Well, we're going to discuss that, but from here to here, how much am I going to drop down total? 30. So if I'm at 10, something's going to happen here. I'm going to start at 10, drop down 30, and I'm going to wind up at something like negative 20 right here. And then that reaction is going to take me back up to 0. Okay? Now, the mystery is what happens in between. What happens in here? Okay? Well, let's see if we can figure that out. Okay? Let's start off with this point right here. Okay, so help me out with this point. What is the value of the load at this point? 0. So what is the slope of the shear diagram at this point? 0. So the shear diagram needs to start out with like a 0 slope, right? Okay? What is the value of the load right here?
0.
No, the load.
Oh. 2.
It's not 2, it's negative 2 because it's going down, right? So what I'm saying is that right here, we better have a slope of negative 2, okay? And so what should be happening is that as we start here and go over, the slope should be decreasing, right? Remember, this is a line, this is going to be a parabola, right? Because we're integrating. So how do we draw a parabola that starts out flat and transitions to this being a slope of -2? Well, what's going to happen is our shear diagram is going to look something about like this. It's going to look like that. That's our shear diagram. So how do I take a shear diagram and how do I take that and determine the moment diagram? What do I need to do? I need to determine the area of this. Dang it. That's kind of hard, right? Because it's all curvy. I wanted rectangles and triangles, and I didn't get rectangles and triangles. I got this hullabaloo, right? But let's see if we can conceptualize what's going on. So would you agree that this is going to be some positive area, this is going to be some negative area, and would you agree at least qualitatively, that, and let's also draw a line right here. Would you agree that our moment diagram, this is what it's going to look like? And maybe what I'll do is I'll put quadratic. So we've got a moment diagram. Start out with that. All right. So we have our foot kips right here. Okay. We're going to start out at 0. Okay. Now, what is our slope of the moment diagram going to be right here?
0.
Hold on, what's the slope of the moment diagram? 10. The slope is equal to the shear diagram, right? What is the slope of the moment diagram right here? What's the slope right here? -20. So, what we should have is something that looks about like this. Something about like that, to where this slope is 10, slope is 0, slope is -20. But I don't know about you, but I think that's about it that I can figure out. That's about all that I can figure out quantitatively. What is this maximum moment? Can you determine this maximum moment quantitatively with this image? I don't think so, because this maximum moment equals that area. I don't know what that area is because it's all curvy, right? Okay. So how are we going to go about this? How are we actually going to figure out some values? Okay. I propose that what we do is this. Okay. We go back to our beam and we cut a section. We cut a section right here. And where is right here? Some distance x away from the left support. So we're going to cut a section. We're going to look to the left. We're going to cut a section, look to the left, and let's see what we've got going on. All right? So let's see if we can figure that out. Okay, so here's our beam. We have a vertical reaction right here. What was that vertical reaction, by the way? 10 kips. And we cut a section such that this distance right here, that distance is x. Okay, and we've got some distributed load. Okay? Now, what we're going to solve for is some unknown shear and some unknown moment. Now, if you would like, you could, I'll usually probably end up leaving it as V and M, but if you want, you could say shear as a function of X, M as a function of X. If you want to use that notation, that's fine too. Okay? Now, let me ask you this. Is that 2? Is that height 2? No, it's not. It's only 2 at the very end of the beam. I need to know what the height is right here. Okay? So how do I determine what that height is? Well, what did we do last time? We said 2 is to 30 as height is to X. Therefore, the height is 2x over 30. So I propose that this height right here is 2x over 30. Now, an easy way of testing that, if x is 0, what is the height? If x is 30, what's the height? It's 2, right? So you're telling me at the beginning of the beam it's 0, and at the end of the beam it's 2, right? Isn't that what it's supposed to look like? So there we go. All right. So the idea is that we're going to collapse this into a single point load. So here's a single point load. Remind me again, what's this distance right here? What's that distance going to be? D. And what is that?
X over 3.
X over 3. Okay? Our force is going to be 1/2 times base times height, which is 1/2 times x times 2x over 30, which is, what is that? X squared over 30. Did I do that right? Did I get that right? So far, so good? So how do I determine V and M? Let's start off with V. How would I determine V? I have an unknown force here. How do I determine? How would I, if I cut a section through a point with any structure, how do I determine the unknown? Sum the forces in the y direction. There we go. So let's do that. Let's sum forces in the y direction. So what do I have? Help me out. I got 10 going up. I've got this going down. And I've got this going down. So 10 going up. I've got V going down. And x squared over 30 going down. Is that making sense? Everybody with me on that? All right, don't hesitate if you got a question. Please don't hesitate. I know this is getting into math land. So, would you agree that would you agree with that? Let's put that up here. Let's look at this equation real quick. If I were to graph that, what would it look like? I mean, I'm not asking for like a perfect, like, you know, Calc 1 representation, but generally, what curve, is this a graph of a line? Parabola. It's a parabola. It's a quadratic. Didn't we say that for a linear load, the shear diagram should be quadratic? It's quadratic, right? Let's see what happens with moments. Let's sum moments at the cut. That's too much. All right. So summing moments at the cut, what do I got? I've got 10 times what?
X.
10x going this way. What do I got going this way? Okay, so I've got 10x going this way. And I've got m of x. And then what else? What do I have? I've got x squared over 30 times what?
X over 3.
X over 3. So I've got 10x equals m of x plus what? What is this going to collapse to? So x squared over 30 times x over 3 is what? X cubed over 90? Did I do that right? So would you agree with this? Right? Now, if I were to graph m of x, what would it look like? If this is a quadratic function, what was this supposed to be, a cubic function? Right? Before we move on, does anybody see something? Anybody see anything with these two expressions?
M of x is the integral of u of x.
Yes, or vice versa. The derivative of the moment is the shear. What is the derivative of 10x? 10. What's the derivative of this? We take 1 over 90. The derivative of x cubed is 3x squared. We get x squared over 30, right? So that's a check that you've done this correctly. That if you derive these equations independently and you take the derivative of moment, you should get shear. I like to use the derivative check more than the integral check because what is the integral of this? It's 10x minus x cubed over 90 plus c. Don't forget that little plus c. That plus c matters. And so in this case, c is 0, but it's easier to differentiate and not have to worry about the plus c than it is to integrate. Does that make sense? Okay. Now, what would be another test that these are right, that these expressions are right? Well, I got another test. How about we break out some Excel? You're engineers. Excel should be one of the 5 food groups. Okay. All right. So I got myself a little Excel sheet, blank Excel sheet. Zoom in a little bit. All right. I'm going to start 3 columns. Let's do X, M, or V and M. Okay? Now, how long is the beam in this problem? 30 feet. So what I'll do is I'll just say 0, 1, 2, and then I will highlight these. Remember the little shortcut? You can hit the little black plus on the bottom corner and drag that down until you get to 30. Okay. Bless you. I want to wait until everybody. Bless you. No problem. All right. Is everybody sort of caught up with me on this part? Okay. Looks like everybody's kind of with me on the same page. Okay. So what we'll do is let's plot out the first function. Okay. So what I'll do is I'll go here and I'll say equals 10 minus x squared over 30. So 10 minus, and we'll say that squared divided by 30, right? We press enter, and then do y'all remember the shortcut to fill them all? And or what you can do is get to where it's the black plus and just double click, and it'll fill them all. So let's just take a look at the numbers. What do we start at? 10. What do we end at? Negative 20. Does that make sense? That's about what it should end at, right? All right. Let's plot this. So what I'll do, look, everybody watch up here. I'll show you a little shortcut. I don't know if you already know this, but I can highlight both of these columns and just go to Insert, and for Scatter, just do the straight line one, and there you go. You don't have to like select it. You can just highlight it. So I'm going to take this and we'll move it up some. Let me move this up here. Now, before we plot the moment function, I want to do a little bit of formatting to this to make it kind of nice. So first thing I'm going to do is I'm going to format this horizontal axis. So I'm going to write, yes?
I missed it. What was the second column there? Leading with the 10.
It's this right here. So it's just 10 minus x squared over 30. Yeah. Don't hesitate if you got any questions. Is everybody else with me up here? If you got any questions, please. All right. So let's do a little bit of formatting on this one. So I'm going to right click. I'm going to do Format Axis. And the shear diagram only goes from 0 to 30. So I'm going to set the minimum to 0 and the maximum to 30. Okay? I think every 5 feet is probably fine for the purposes of what we're trying to do here. The other thing I'm going to do is under labels. So I'm going to go under labels, and I'm going to say, instead of label position, I'm going to put that low so that the labels aren't in the middle of the shear diagram and I can actually see what's going on. Okay? The other thing I will do is I will add some axis titles, and I'll say this bottom one, we'll call it distance cross beam. We'll call that in feet. We'll call this shear. And we'll name this shear diagram. Didn't take a lot of work, and now it's pretty professional, right? I'm going to move that over a little bit. There we go. Let's zoom out so everybody can kind of see what's going on. All right. Give everybody a couple minutes. I want to see how you're doing on this. Looking good. Looking good. All right. I like it, because I'm going to show you some Excel tricks here in a little bit. Okay? Now let's take a look at the moment. Let's do the moment. So before you do the graph for the moment, don't plot the moment yet, because I'm going to show you something. Okay? All right? Let's do the expression. Let's just do the equation. Okay, so here's our moment expression right here. So it equals 10 times x minus x cubed over 90. And double click. So does it start at 0 and does it end at 0? Yes. Right? Now, everybody watch this. Okay, watch this. Watch up here. So here's what I'm going to do. I'm going to copy the entire shear diagram. So copy the whole plot. Now, watch what happens when you copy the plot. See how it highlights these columns? Just take the column and drag it over. Boom. And now it replots the whole thing. So now I have a whole new plot. All I have to do now is relabel it. And boom, there's my moment diagram. I'll zoom out a little bit. Tell you what, one other thing I'm going to do, you don't have to do this, but one thing I'm going to do, I'm going to click my axes, and I'm going to make them like dark. I'm going to make them kind of thick so we can kind of see what's going on. Oh, wrong one. shape outline black, make the weight a little bit bigger. Just so we can kind of see what's going on the screen. You don't have to do that, but I'm just doing that here just to kind of show you what's going on. Pretty easy, right? Now, does everybody, if there's any, I did that kind of fast, so if there's any steps that you all are having issues with, let me know, please. This is what we're here to do. Now, first off, do these pictures look great? I mean, what did we kind of conceptualize here in our calculations? I mean, we conceptualized this. This is what we put together in our brains, and this is what the math is telling us. That looks pretty good. There's a couple things, though, that are kind of interesting. How many of you would have guessed that this distance on the shear diagram was 20? And it's not. It's interesting, isn't it? It's not 20. I'm going to show you why here in a second. But I propose to you that distance is correct because look, where the shear diagram is 0, the moment diagram is maximized. Very interesting. What is the maximum moment that we're getting on our moment diagram? What is this? 115-ish? Is everybody kind of seeing that? Let's see if we can figure that out without Excel. Now we're going to go back to Calc 1 land a little bit. Okay? Does everybody have this? I can pull this back up if you need. Has everybody got this? Okay, let's go to Calc 1 land. Let's see if we can figure that out. How do we figure out where the maximum is on a function? Well, the maximum occurs where its derivative is 0, right? So, how about this? Maximum moment. Mmax occurs where the derivative is 0. What is the derivative of moment? Shear. So therefore, set shear equal to 0, solve for x. So what do we get? Shear was 10 minus x squared over 30. So 0 equals 10 minus x squared over 30. So 10 equals x squared over 30. Just add the x squared over 30 on both sides. So x squared is 300. X is the square root of 300. What is the square root of 300?
17.3.
17.32. Does that match what we were getting in Excel? It's about right, doesn't it? So where the shear crosses 0 is where this function equals 0, not the centroid of the load. They're not the same thing. The shear diagram is plotting the change in vertical forces along the span. So it doesn't quite equal 2/3. You think it would initially, but it doesn't. So 17.32. So therefore, Mmax is going to be the moment at 17.32 feet. So that's going to be 10x minus x squared over 30. Or x cubed over, or sorry, 10x minus x cubed over 9, sorry. Actually, let's do it like this. And what do we get when we chug this out? see what I'm doing here? So I'm taking the derivative of moment, setting it equal to 0, but I've already got that because that's the shear. So solve here and I get 17.32. I take that x value, plug it into my function, and that'll give me the maximum, right? That's what you learned in Comp 1. If you want a maximum of a function, take its derivative, set it equal to 0, solve for x, take that x value, plug it into the function, right? We don't need to do first derivative tests or anything like this because we can look at our moment diagram and see it's going to be a maximum. We know it is. So what do we get for this?
115.47.
115.47. Do I have a second on that? And does that match what we plotted? Well, again, we can eyeball it and we can say it's about 115 point, something. And if we look at our columnar values, what are we getting? Look what happened here. So this is at 16, this is 17. Look at what we got at 17. So at 17, we got 115.41. At 18, we got 115.2. So it's going to be between, somewhere around this value right here. We got about 115.4, Sounds about right, doesn't it? Not too challenging, is it? Make sense? Okay, so on the next homework assignment, what you're going to do is you are going to derive a similar function and produce a similar plot. I want to mention a couple things. This homework is easier than what we did in class, okay? But the homework that I'm assigning today is not a triangular load. It is not a triangular load. So if you try and apply the whole x over 3 or the whole 1/2 base times height, that's going to be wrong, okay? The idea is those were the principles we applied to this problem. I want you to apply different principles to the problem I'm assigning today. Again, the problem's easier. If you can do this, you can do the homework problem. The problem I'm giving you on the homework is easier. So, but again, it's Excel land for this homework. Does that make sense? All right, anybody have any questions on this? All right, I'm going to pull up the code one more time, and I will see you all.